Let's talk about the mean and the standard deviation of the binomial distribution. Um, we had explored this particular binomial situation before, a family of five. Each kid has the probability of 0.25 of having type O blood, and we have these particular probabilities associated with each of the values that the random variable takes on. We can see by looking at um, this histogram that the shape of the distribution is, in this case, skew right with that tail on the right-hand side. We may explore the question of center. Probably the easiest way to get to center is to talk about the median. Um, let's see, here's about 23%, here's about 40%. That puts us over 50%. So we hit over that 50% threshold at 1. We might talk about the spread using the range. That's pretty easy. Range is 5 minus 0, which is 5. But could we get at the mean? Could we get at the mean? Well, down below here, we see we have a formula. The mean of a random binomial variable x is n times p, and the standard deviation of the random variable x is the square root of n times p times 1 minus p. So we might say that the mean here is 5 times 0.25, which ends up being 1.25. We might find out that the standard deviation is the square root of 5 times 0.25 times 0.75. And if you throw that into the calculator, you get that the standard deviation is 0.968. Now, you're just taking my word for it that these are the formulas. Let's try to look at this using some technology. And I'm going to switch over to the nspire calculator. All right, I'll create uh, a new document. And in that new document, I'm going to create a list and spreadsheet. And in this column, I'll put the number of kids with type of blood, and it could range from 0 to 5. So I'm going to do something I haven't done before, and that is I'm going to go into this cell, the one below the name cell, and we're going to put in all of the numbers from that probability distribution. I'll do that doing menu, statistics, distributions, and we'll choose the distribution binomial PDF. And there's 5 trials, and the probability of success on each individual trial was 0.25. And if I just hit enter, then all of those numbers from that probability distribution are now entered into this list. And I'm going to give this list the name probabilities. If I then create a page, calculator page, and say, well, I would like to find out from that distribution, what is the mean and the standard deviation? I'd go stats, stat calc, and one variable statistics. I've only got one list of data. That list of data is called number, and the frequency list is the probabilities from the binomial distribution. And if we take a look at this, we see that indeed that the mean is 1.25 and the standard deviation is just as we said, 0.968. All right. So these formulas are on your formula sheet, but you should feel comfortable using them. Remember that these formulas only work for binomial distributions, but don't try to use them with any other distributions. All right, let's take a look at some of these ideas in action. It says Mr. Bullard's AP Statistics class did the activity on page 340, where students were asked to determine whether they can taste the difference between bottled water and tap water. There are 21 students in the class. If we assume that the students cannot tell tap water from bottled water, then each basically is guessing with a 1/3 chance of being correct. Let X be the number of students who correctly identify the cup containing the different type of water. I'll explain why this is a random variable. Well, B, it's binary, either you're right or wrong. Binary, give yourself a check mark. I, each trial is independent, meaning one trial does not affect the other trials. N, there's a set number of trials. In this case, the set number of trials uh, is the 21 students that are participating. And S, there's the same probability of success on each trial, and that is 1/3. So let's find the mean and the standard deviation of X and interpret each in the context. All right? Well, the mean is N times P, which in this case is 21 times 1/3, which is equal to 7. And what does this mean in the context of this problem? Well, over many groups of 21 students, there is an average of 7 correct guesses. There we go. And there's our finding the mean and interpreting the mean. What about the standard deviation? Well, the standard deviation is going to be the square root of 21 times 1/3 times 2/3. And let's go ahead and put that into the calculator. I'll uh, scroll down here, get to an open line. So we'll do the square root of 21 times, and then I'm going to do control division to make a fraction, 1/3, and we'll multiply that again by control division, 2/3. And that calculator gives us that answer. I'd rather see it in decimal form, so about 2.16. 2.16. And what's the meaning of this? Well, again, over many groups of 21 students, the number of correct guesses differs from the mean by 2.16, and that's on average. All right, so there we have it. All right, of the 21 students in the class, 13 made correct identifications. Are you convinced that Mr. Bullard's students can tell bottled water from tap water? Well, let's ask the question, what's the probability that you would get 13 or more guesses right? 13 is one outcome, but let's lump them on with all the outcomes more extreme than that. And that's going to be a question for uh, the calculator. We want the Binomial PDF with 21 trials, 1/3 of a chance per trial, and we're going to want to know probability of 13 or more. So this is actually 1 minus, and we're going to subtract off the 12. All right, so let's see. Menu, probability, distributions. And again, we want binomial CDF. Okay, I have the things wrong there. So we have 21 trials. We have a 1/3 chance of success on a trial. Our lower bound is 13, and we want the upper bound to be 21. That will give us the answers from 13 to 21. and we got 0.0068. So let me change my writing here. This is from 13 to 21. I was using an old calculator notation, which again was 0.0068, which is certainly less than our value of suspicion, of our value of that's different of 5%. Therefore, it is unlikely. It's unlikely all the students were guessing. There we go. All right, let's take another look at another example. Uh, so remember that we had a thing about multiple choice quizzes. In that situation, there were 10 questions. The probability of success on any one try was 1/5, and X was the number we got right. So we said X is a binomial variable, 10 trials with a 1/5 chance of success. And what is mu of X in this case? Well, it's again n times p, which in this case is 10 times 1/5, which is 2. And what does it mean in context? Over many groups of, in this case, 10 questions, the number of questions answered correctly was 2 on average. Okay, what about the um, standard deviation, which again would be 10 times 1/5 times 4/5. Put that into the calculator. Square root n times, and then again I'll make the fraction 1/5 times, again I'll make the fraction 2/5, and I'll hit control and then enter, get the decimal version of that. 0.8944. 0.8944. And what's the interpretation of that? Well, over many groups of 10 questions, the number questions answered correctly varied, or I'll use the word I used before, differed from the mean by 0.8944 on average. Okay, so what's the probability that the number of correct guesses is more than 2 standard deviations above the mean? Well, geez, the mean is 2, and if I add 0.844, then I guess the question is, what's the probability that X is greater than 2.8944? Now, to answer that question, I'm going to go into a binomial CDF again. Menu, probability, distributions, and again, we're going to want the binomial CDF, 10 trials, 1/5 chance of success in each trial, lower bound. Well, we need to be bigger than 2.89. So I guess my lower bound is 3 and my upper bound is 10. And we would want to put onto our paper this binomial CDF command, 10, 1/5, 3 to 10. And that happened about 32, right? About 32% of the time. Oh, I'm sorry, screwed this up. This is supposed to be, let me make the change in red so you can see it. This is supposed to be 2 standard deviations. 2 standard deviations is 2 plus 2 times, let me go grab that standard deviation, is 3.7888. Okay, so this is going to be bigger than 3.7889, which means this number is going to be not from 3 to 10, but 4 to 10. So I'm going to go here. I'm just going to change this to 4. And that drops it down to about 12%. 12.09%. All righty. Okay. Let's go ahead and look at a next section, which is about how we might, I don't know, cheat a little bit. I think that's the wrong expression, but we'll use it anyway. It says, do you remember the NASCAR card and cereal boxes problem that we did before? There are 5 different cards in the boxes of cereal, and the cards are randomly distributed. Let's suppose that there's 20,000 of each card in the cereal boxes for a total of 100,000 different boxes with cards in them. Let's say if the person bought 6 boxes, what's the probability of getting no Danica Patrick cards? Well, if we let X be the number of Danica Patrick cards, um, we officially cannot say this is a binomial situation because since we're sampling without replacement, each of these trials are not independent. Okay? That each of the trials, the probabilities change just a little bit on each trial. And here's me ever you go, after the first card's pulled, there's fewer cards in the box and fewer cards um, that aren't Danica Patrick. We get that number. But let's just say for an instance, we say, well, what if we would have calculated this binomial? What if we would have done that? That's the binomial of the exact outcome of 0 and probability, distributions, binomial PDF, because we're only looking for exactly 0. There was 6 trials, and the probability of success on each trial was 1/6, right? And we're looking for only the outcome of 0 successes. All right, so there's our number, 0.334898. 0.33, I'm sorry, screw that up again. There are 5 different cards. So probability is 1/5. Try that again. 0.262144. 0.262144. All right. Now, look at us doing it the right way. We get this number. And here's we doing it the quote unquote wrong way, and we get that number. And the only difference is the last digit. which hardly on a six-digit number matters. So here's what we're going to say. In practice, binomial distributions give good approximation as long as we don't sample more than 10% of the populations. So yes, these probabilities change, but they don't change enough to make a material difference in the answers. We say that this situation, the events are not independent, but they're independent enough. So we say, we call this the sampling without replacement condition. It says if you're doing a simple random sample from a population of size n, so this is the population size, you can still use the binomial distribution as long as the sample size is less than 1/10 of the population size. Now, we saw it in the card example how it worked. Here's how it would not work if we didn't follow that rule. Let's say you have a drawer, and in that drawer, there are 8 AAA batteries, and 6 of them are good. You choose 4, hoping that all 4 of them are good so that you can put them in your calculator. What's the probability that all 4 batteries work? Well, if we think of this as binomial, which it isn't, we would think of it as 4 choose 4, probability of success, probability of failure, and we get that number. But the actual probability is much different. Why? Well, we didn't follow the 10% rule here. Our sample size was 4. Our population size was 8. Well, is 4 half of, let's see, 8 divided by 10, 0.8? No, 8 is not less than 0.8. And so we fail to meet the 10% condition, and that's why these two probabilities are so very, very different. That because we're sampling, since we're sampling 50% of the population, which is not less than 10%, it gives us values that are not quite right. All right, last topic for this binomial distribution stuff. It says, as n gets larger, something interesting happens to the shape of the binomial distribution. What do you see? And what I see is that this is left skew, but this looks normal. And the difference between our first step and our last step is the sample size. Here's our general rule. It says, suppose X has a binomial distribution with n trials and probability of success P. When n is large, when the sample size is large, the distribution of X is approximately normal using the same mean and standard deviation formulas that we used before. Okay. This only works though if n is large enough. And we're going to say for the purpose of our class that n times p has to be greater than 10 and n times 1 minus p has to be greater than 10. Now, n times p, if you remember correctly, well, that's the expected number of successes. N times 1 minus p is the expected number of failures. Okay, so we're going to say we can use this normal distribution estimation as long as we expect at least 10 successes and 10 failures. Let's take a look at this in action. It says sample surveys show that fewer people enjoy shopping than in the past. A survey asked a nationwide random sample of 2,500 adults if they agree or disagree to the statement, I like buying new clothes, but shopping is often frustrating and time consuming. The population that the poll wants to draw a conclusion is all U.S. residents aged 18 or over. It says, suppose that we know that exactly 60% of all adult U.S. residents would agree to the statement. Now, let X be the number of people who would agree. Show that X is at approximately binomial random variable? Well, first of all, is it binary? Well, every trial ends in either success or failure. So that makes it binary. Okay, success meaning they agree to the statement and failure meaning anything else. Is every trial independent? What we're going to say is since n, which is equal to 2,500, is less than 1/10 of big N, which is all U.S. students or residents age 18 or over. Since we meet that criteria, we're going to say we're independent enough. Okay? Do we have a set number of trials? Well, our set number of trials is the same as our sample size. And again, N is 2,500. We meet that criteria. Is the probability of success the same on each trial? Well, P is equal to 0.6. We're going to say yes. We're going to say that it's approximately a binomial random variable. Now, do we meet the conditions for a normal approximation? Well, N times P, which is 2,500 times 0.6, well, that ends up being 1,500. And then we ask the question, well, is 1,500 greater than or equal to 10? Yep, we expect more than 10 successes. What about N times 1 minus P? Well, that's 2,500 times 0.4, and that ends up being 1,000. And 1,000 is also greater than equal to 10. Therefore, the binomial distribution can be estimated by the normal distribution. Okay, and it says, okay, use the normal distribution to estimate the probability that 1,520 or more of the sample agree. All right, well, let's draw that normal distribution. Remember, we said it was centered at 1,500. That's expected number of successes. We probably need to find the standard deviation. Remember, the standard deviation formula is the square root of n times p times 1 minus p, which is the square root of 2,500 times 0.6, in this case, times 0.4. So we get 2,500 times 0.6 times 0.4, and we get 24.49. I guess it rounds up to 24.5. 24.50. So if we go up one standard deviation, we're at 1524.50. If we go up another standard deviation, we're at 1549. If we go down one standard deviation, we're at 1474.50. But we're interested in the probability of 1520, which is about there, or above. Probability that X is greater than or equal to 1520. Well, let's put this into our normal distribution calculation. Probability, option 5. Distributions, option 5. But we want the normal CDF. Our lower bound is 1520. Our upper bound is infinity, which is under the pi key. Our standard deviation, sorry, our mean was 1,500, and our standard deviation was 24.50. And there we have it, 20.72%. 20.72%. Sorry, should put the decimal point there. And we should remark that this is normal CDF, lower bound 1520, upper bound infinity, mean of 1500, and standard deviation of 25.50. And then we remark, this is my lower, this is my upper, this is my mean, and this is my standard deviation. There we go. All right, you did an estimate using the normal distribution. And that is the end of the 631 lecture.